All right, so we're going to be talking in our next section about chemical and mechanical senses. Chemical being the senses that actually take in chemicals in order to create some sort of perception in the brain, meaning taste and smell. And then we're also going to talk about mechanical senses, so things that we can actually feel on our skin, touch, temperature, and things like that. Now, before I go to the next slide, which kind of introduces this, I'm going to warn you, the picture on it is very strange. There it is. So this is called a homunculus, which means little man. And what he represents is the amount of cortex in our somatosensory cortex. If you remember, that's that headband that goes across the top of your head. In front, you have the motor cortex, and then right behind that, you have the somatosensory cortex. And this image kind of represents how much space is given to different body types. So he's exaggerated with shape of his body by how much cortex is devoted to sensation of those areas. So his lips, tongues, ears, nose, eyes get a lot of space on the cortex. Hands, of course, you have a lot of close dexterity with the hands. Feet, and of course genitalia. But the legs, limbs, and torso, they don't get a whole lot of space. So they're not as defined or as well represented in our cortex. So that's why he looks so funny. I know it's very strange, but it is a good visualization, so that's why I keep it. Plus, everyone gets a good laugh. All right, so first we're talking about somatosensation. So again, soma, if you remember from before, means body. So this is the sensation of the body and the body position. So we're going to be talking about bodily sensations that come from our skin, muscles, and joints. And this is processed by the brain's somatosensory cortex. Again, that thin band of cortex, it's like a headband across the top of your head, right behind the motor cortex. This is part of our parietal lobe. We have receptors within our skin that provide information about touch, pressure, and temperature. We have receptors within our muscles and joints that provide information about position and movement, strain as well. So if you're picking up a weight, you can feel the strain on your muscles. And you also know where your limbs are within space. And both of these different types of pain receptors can actually send pain signals back to the brain. Now, I want you to just quickly kind of do a thought experiment with me. Would your life be better or worse if you were unable to feel physical pain? Think about that for a second. If you couldn't feel physical pain, how would your life be different? Would it be easier? Would it be harder? What things maybe you would have done differently if you couldn't feel physical pain? So as you think about that, I want you to pull up a video of the girl born without pain. This young lady, she was born without the receptors in her skin that feel pain and feel temperature. As you'll see in the video, it had some really dire consequences for her life, but she's doing really well. So check out that video, and I want to see kind of how you feel about that after, like this thought experiment of being without pain, how that maybe has changed by watching this video. So within our skin, we have different layers of tissue that allow us or hold receptors for touch, temperature, and pain. So the outside of our skin is called the epidermis. This is a layer of dead skin cells, and it's thick and it helps protect us from outside elements. That's where we have hair that kind of comes up. We have our pores. And those pores can, of course, get infected and cause pimples and zits and all those good things. We also have the first kind of layer where we have some blood vasculature going on in there. Below that, we have what's called the dermis. That's where we have different pain receptors and other different types of nerve endings. And then below that, we have what's called subcutaneous tissue, and that's where we have fat, the nerve endings that travel back to our nervous system and our spinal cord and back up to the brain. And then, of course, a lot of blood vessels. So in the dermis, we get a lot of these different nerve endings. They all have these kind of funny different names. We have Merkel's discs, free nerve endings, messeners, corpuscle, hair follicle receptors. So if you touch the hair on your arm, you can actually feel that without touching your skin. There's little receptors in there that feel their movement. That's really good because you can feel maybe if an ant is going across your skin, but it can be also really annoying. Like you might feel like you have a spider web on you when it's really just a hair that's come off your head. And that was really annoying, of course. Pacinian corpuscles and Ruffini endings. So we're going to be going through all of these in the next slides. So, again, the outermost layer is a thin layer of dead skin cells with no receptors. That's called our epidermis. And then in the middle and fatty layers of the skin, there's a variety of different receptors. Merkel's discs, they sense pressure on the skin. So if you press down on your arm, you can feel that that's your Merkel's disc at work. The Messner's corpuscles, they sense pressure as well. Hair follicles sense hair movement. Pacinian corpuscles, they sense pressure and vibration. Ruffini endings, they sense skin stretching. So if you like maybe stretch your hand or your arm, or maybe pull up on some of your skin, you'll feel that skin stretch. And then free nerve endings, they pick up temperature and pain primarily. So that little girl in the video, she doesn't have the free nerve endings that you and I have. All these receptors will send their electrical signals back to neurons within the spinal cord, which then brings that information back up to our brain. Now, there's a really interesting theory about pain called the gate control theory of pain. So if we have an event or an injury that occurs to our body, let's say you're walking around, you trip and you stub your toe and it really, really hurts. There are some factors that we say will open the gate, so allow more pain to be sent up to the spinal cord and be processed by the brain. And there are other factors that can close this gate, or essentially deaden the amount of pain that comes up and it is experienced. So if you're in a period of chronic stress, you're more likely to feel that pain more acutely, like it's going to hurt more. But if you're maybe distracted, if you're under a high level of arousal, so maybe you're fighting someone off, and the reason you're running is that you're trying to get away from a bad guy, those things are going to kind of keep your mind off the pain, and it will lessen the pain. And it changes how you experience it. So how you experience pain is always dependent on a variety of factors, and that factor is called that gate control. So how open that gate is or how closed that gate is. So, imagine, you get stabbed in the stomach. Like, that's going to hurt. But again, if you're in the midst of a battle, or you're trying to save your child's life, like, you're probably not going to notice those things. But maybe you've had a bad day and you bump your knee and now it just aches all day. And that chronic stress and that bad mood can open that gate and make you feel that pain more acutely. Endorphins, we've talked about a little bit back in chapter 2, but endorphins reduce pain by allowing to close the gates, they help to close the gates that allow for painful nerve impulses to go back to the brain. They're opiate-like, so they actually are released and they cling onto those opiate receptors and they deaden that pain. They're released in a variety of circumstances. It could be anything from traumatic injury, sustained physical exertion, such as a runner's high, and also pleasant experience such as sexual activity and listening to music. So there's a lot of different ways that you can release endorphins, oftentimes doing something physical and stressful, and then like completing that activity, like bungee jumping or whitewater rafting. You get that rush after you're done, and those are the endorphins. And you feel great afterwards, and your body doesn't hurt as much as you maybe expected it would. Maybe the next day it does, but that's the endorphins that are deadening that pain. Now within our ear, remember we talked about, I mentioned we had these like little circular things above our cochlea. This is our vestibular sense, and this is also in our inner ear next to our cochlea. And so here's an image with the cochlea right here. It's kind of a different turn of the cochlea. But up here is what we're talking about, these semicircular canals. And these send signals back to the vestibular nerve, just like we have the auditory nerve coming from our cochlea. And these semicircular canals are sensitive to position, acceleration, and rotation movements. So if you get up and you spin around 10 times afterwards, your brain's probably like, woo, what did I just do? That's your vestibular sense. That's this inner ear, these semicircular canals that are sensitive to your body position. And that change, especially that rapid rotation, which makes you feel dizzy temporarily. So the vestibular system is a set of fluid-filled sacs called the otolith organs, and they're sensitive to movement, acceleration, and gravity. The otolith organs, they contain tiny crystals in a soft gelatin-like mass. So if you have a rapid tug of gravity or rapid head movements, it can cause the mass to shift. So if you shake your head back and forth, you might feel a little weird for a minute. If you go on a roller coaster, that drop, even if you're doing like a roller coaster virtual reality, like you see that drop, even though you're not actually dropping, your brain is interpreting that, and you're gonna feel like that drop in your stomach and then in your head. Um, this movement of the crystals will stimulate hair-like receptor cells that allows us to sense gravity, acceleration, and movement through space. And the semicircular canals are the sensory organs for balance. So our head movements cause these fluids to swirl about, and it helps us kind of know where we are and how we're moving. Um, if you're a person who gets car sick or seasick when you're on a boat, what's going on is that your eyes are doing something and your brain is seeing something and your body's doing something like moving, but your brain hasn't caught up to what your vestibular system is actually sensing. So of course the best way to avoid this is to not look down at something small like reading on your phone or reading a book. So look out at the horizon and kind of help your brain match up what it's sensing in the vestibular system with what it's seeing. But it doesn't always work for everyone. I know I'm super sensitive to motion sickness, so I have to take precautions. I take Dramamine, but there's a variety of different things you can do. There's different pressure points. There's different foods you can eat that will help. Just different kind of techniques. But for some people, they're just very sensitive. Other people just aren't very sensitive. And it really depends on the individual. And that can change throughout life. If you were really sensitive as a child, you may no longer be so sensitive today. Now we have our sense of smell. So we have olfactory nerves. These are special nerve endings that sit inside your upper nasal passages, and they have these little receptors that when chemicals float through our environment, they float up and they grab on from those receptors to those chemicals, and then they fire signals back to our brain through our olfactory nerve, and then that reaches our olfactory bulb, which is kind of on the base of the brain below the frontal cortex. And then from the olfactory bulb, it then goes to our frontal lobe for processing. And it's interesting because smell is a really durable sense. It's very closely linked with memory. So you maybe like walked into a space before and been like, wow, this reminds me of summer camp or my grandma's house. And like these smells, like they just pull you back. It's really quite amazing how impressively strong the sense of smell is linked to memory. So it is really interesting also too that when you're smelling something, you're actually smelling chemical properties of that thing. So if you're smelling a rose, there's chemicals coming off that rose, usually volatile oils and sort of essences that kind of come off of that from the pollen and from the nectar that we actually bring up into our nasal cavity. So if you're smelling something, you're actually getting particles of that thing into your olfactory sense. That's pretty cool when I'm talking about roses, but maybe not so much when we're talking about farts and poop. So kind of take it with a grain of salt. Now the interesting thing is that our receptor cells are for olfaction are one of the quickest turning over cells in our nervous system. We used to think as scientists that no nerves actually ever regenerate once they're created in infancy or prenatally, but these actually regenerate over and over again. And now we're discovering that a lot of different cells in our nervous system actually do regenerate. So olfaction, that's the technical word for smell. These are the receptors that are located in a thin layer of cells within the nasal cavity. The olfactory receptors regularly die and then are replaced by new receptor cells lasting 4 to 6 weeks. So that's a very quick turnover. The cells at the base of the receptors are responsible for producing the mucus surrounding the receptors. The mucus is actually really important. If your nose is really dry, you can't smell very well because the chemicals can't get stuck in anything. You kind of need that moist layer for them to kind of cling on. If you've ever been somewhere where it's really dry, like in an airplane, you can't smell as well, which is one of the reasons why airplane food doesn't usually taste very good, because the air is so dry, you can't smell as well. Same thing happens in the winter up north when the air is really dry. People will typically wear heavier perfumes or smellier lotions than you would in the summer, because otherwise it's just too overwhelming when the air is moist in the summer. One branch of each of these receptors interacts with the molecules dissolved in the mucus. The other branch carries information back to the central nervous system as part of the olfactory nerve. The olfactory nerve fibers synapse in one of the two olfactory bulbs located below the mass of the frontal lobes. So like I said, it's kind of like right down in here. Now, other animals have more complex nasal passages and more space that's devoted for their olfactory sense, and they have more receptor cells. Like dogs have, especially if you look at dogs who are known for their smelling, like bloodhounds and things like that. If you look inside their nasal passages, now you can't do this just normally, but if you look up videos on this, they have much more like wrinkled nasal passages, which allow them to have more receptors, and then their olfactory bulbs are larger than us as humans. Even though sense of smell is still important for us humans, it's way more important for a lot of other animals than it is for us. A lot of animals, sense of smell is one of their primary senses, where for us, vision and audition is more central to our day-to-day lives. Then we have taste. So this is an up-close image of the surface of essentially a cut of the tongue. Kind of the surface would be up here. We have supportive skin tissue of the tongue, and then we have these receptor cells, and then in here we have the little nerve endings. So the surface of the tongue has a lot of receptor cells. These are our taste buds, but throughout our mouth we actually have receptors. That gets transmitted to our medulla, then our thalamus, and then our parietal lobe. So again, medulla kind of in the brainstem, thalamus right in the middle of the brain, and then it goes to the parietal lobe for further processing. So taste receptors are located on taste buds, located in bumps or polypi, which is the technical name, located in the tongue. So if you step out your tongue and you look in the mirror, you can see these little bumps, and those are your taste receptors. The purpose of this sense of gustation, the technical word for taste, is to protect us from eating poisonous or spoiled foods. So things that taste rotten we're not going to want to eat, but they attract us to foods that boost our chances of survival. So things that are sweet and salty, those provide us with essential nutrients that we need in order to live, to get the correct calories and nutrients that we need to survive. Most of us are familiar with the four major categories of taste: sweet, salty, bitter, and sour. You may have seen those maps of the tongue where they're like, oh, salty's on the sides and bitter's in the back and sweet's on the tip. That's actually complete crap. That's pseudoscience. All throughout your mouth, you can actually taste all those different categories. There's actually now what's a fifth sense of taste, which is known by the Japanese term umami. For the longest time, scientists weren't sure if it was real, but now they're relatively certain that this is a real thing. It translates to being savory or meaty. We kind of crave things that have this like unctuousness to it. So, of course, meat has meaty flavor, but so do things like Parmesan cheese, tomato paste, mushrooms, soy sauce, Worcestershire sauce. Like these are the flavor enhancers that we use to make our food taste better. If you've ever heard of MSG, probably like seeing signs of Chinese food that says, we don't use MSG. That stands for monosodium glutamate. Now, glutamate is the actual compound that's found in all of our food that has this umami flavor to it. So meat, soy sauce, Parmesan cheese, things like that. They have a lot of this glutamate in it. Essentially, it's an amino acid that our taste receptors pick up and are like, ooh, that's delicious. So a scientist in Japan, or I think it's Japan, that or China, he was able to isolate that and make it into a powder, like a little crystalline. It looks like sugar or salt, and it's sold commercially as MSG. Now, it's gotten a really bad rap as being harmful, causes headaches and stomach aches and things like that. But really just a flavor enhancer, just like any other spice would be. There's no actual research that shows that it causes any problems. And Chinese food has gotten a bad rap for it because in Asia they do use it a whole lot. You can go to a lot of Asian markets and buy a bag of MSG. I actually have some in my pantry. I use it when I'm cooking here and there. If I need something just to make the flavor pop. You only need a little bit. A little bit goes a long way. But a lot of people think it's just absolutely terrible, and they only go to restaurants that say that they don't use MSG. But the thing is that MSG is actually added to a lot of our foods. Like Doritos have MSG, Cheez-Its have MSG. a lot of just pretty much any prepackaged foods you're going to get at the supermarket are going to have MSG included because it enhances the flavor. It makes us want it more. So don't get concerned about MSG. If you see it at a grocery store or you see it at like a specialty market, pick it up, try it in your food. You can put a little bit on your tongue. You'll get that like savory punch. It's kind of interesting. It's a neat substance. Pretty much any chicken broth is going to have MSG in it. So check it out. Don't be afraid of it. The whole Chinese food syndrome is actually just pseudoscience. There's no research to back that up. Also on our tongue, we have receptors for capsaicin. This is the active ingredient in hot peppers. So by activating these receptors, it causes a perception of spicy heat. So you feel like your mouth is burning. So peppers actually developed capsaicin in order to keep mammals from eating their food. So most animals won't eat spicy peppers. The reason that pepper plants don't want us eating this is when we're chewing up, we break down their seeds by chewing on them, and then our digestive system breaks them up. But birds, they don't have these receptors for capsaicin. So when they eat peppers, they don't get the spicy heat, and then they also don't break down the seeds. So when they poop it out, then the seeds get spread, and the plant can grow somewhere else. Now, we humans are a masochistic group, and so we started eating them for their spicy kick, and we've developed really, really spicy peppers and sauces and things like that. It's interesting. I don't know about you guys. I'm a big chili head. I like to eat spicy foods. My husband is extremely crazy when it comes to spicy foods. We actually grow a lot of really, really intensely spicy peppers in our yard. Peppers are essentially heat level is rated on a scale using Scoville units. And so 0 Scoville units, it's like a bell pepper. There's no heat to that. Jalapenos have about 1,000 Scoville units. I believe habaneros are like 20,000. And then Carolina Reapers, which are currently the hottest peppers, have over 1 million Scoville units. I grow those. They are crazy and stupid hot. But it's people really get into kind of building up their heat tolerance, and it's one of those things that it's kind of like that pain turns into pleasure kind of thing. Those endorphins get released, and it becomes a pleasurable sensation to have that tingle going on in your mouth. Now, I want to connect smell with taste a little bit. About anywhere, I don't know the exact number. I think it's anywhere between 70 and 90% of what we taste actually comes from our sense of smell. You can test this out if you have like Skittles or Starburst or some other candy with like a fruity flavor. Before you put it in your mouth, plug your nose. Then put the candy in your mouth and chew on it for about 10 seconds, kind of get all the juices flowing, and then unplug your nose. And you're going to get essentially this sweet, 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 maybe a little sour, and you unplug your nose, it's going to be like poof, like this huge burst of flavor hitting your face. And that's a sense of smell that you've previously blocked now being opened up, and it allows the full flavor because of the smell to be recognized by your brain. So taste is in part smell. Okay, so the bumpy texture of your tongue, which is the result of the presence of polypi, contains somewhere between 1 and 100 taste buds, so quite a few. And each one of those little bumps are between 1 and 100 taste buds. Each taste bud contains between 50 and 150 receptor cells, which extend tiny hair-like cilia into the saliva that interact with dissolved taste stimuli and transduce the resulting information into neural signals. So just like our nose needs mucus, we need saliva in our mouth to help dissolve these compounds that our tongues can actually pick up. Just like our olfactory receptors, taste buds have a limited life before they get replaced. So again, it's another nervous system component that actually has a lot of turnover and replacement. There's also a really interesting video that I've placed in the playlist about wine tasting competitions that are done at certain colleges. So using smell and taste to pick out not just, oh, it's a Chardonnay, it's a Merlot. Like they will tell you the exact type of wine, where it's from, what year. It's very bougie, but also really fascinating. So go ahead and check that out in the playlist. All right, so I'm going to stop here because next section we're going to be talking about perception.